Hey, good morning, everybody. My name is Yapin Dan. I'm a faculty member at the University of Michigan, Shanghai Jiaotong University Joint Institute at Shanghai Jiaotong University in Shanghai, China. And today I'm going to present the device principle of high gain photoconductors. Photoconductors are actually the simplest devices, semiconductor devices. It only has a semiconductor in contact with two metal electrodes and form this is sort of like a resistive device. So when you illuminate light, so the electrode pairs were generated inside and then the resistance will decrease or the conductance will increase. So using this as a photo detector, it's kind of photo detector. Although this sort of device is very simple, but it has a very interesting phenomena. The interesting phenomena is the gain is extremely high. It can be easily reached like 10 to 5 or 10 to 8. Okay, as we know, regular photo detectors, for example, PIN photo detector, their gain normally is 1, will not be higher than 1. So the gain for photoconductor is extremely high, especially in particular for those nanoscale photoconductors. The gain will also define the same as in the normal way. So the gain, the photo gain G is in quantum efficiency. So that's defined as the number of photon carriers, electrical pairs, excess electrical pairs generated, divided by the number of photons are actually instant into the semiconductor and absorbed by the semiconductor. Just follow this definition, their gain is extremely high. So that's why a lot of papers investigate this new phenomena on nanowires, quantum dots, thin films, like more recently on 2D materials. So in this talk, I'm gonna divide my talk into two parts. First, I'm gonna review the classical photoconductive gain theory, and then we present some of my new research on this topic. We find that photoconductor actually intrinsically has no gain. Okay, let's just give you some basic semiconductor physics concepts. So carrier generation or recombination. Giving a piece of semiconductor, for example, is the N-type. It has a lot of electrons in the conduction band. It has some holes in the valence band. Now, let's suppose you have some light illuminate on this semiconductor, and the photon energy is higher than the band gap. Then in this case, the electron in the valence band can absorb the photon, then excite it into the conduction band. So you create an excess electrons in the conduction band. At the same time, you create a hole in the valence band. So as time going on, so more and more of these electrons will be generated, continuously absorb the photons, instant photons, and more holes will also be created also. But this will not go forever. If this is for go ever, then there will be like infinite number of this excess carrier in the semiconductor, because at the same time you create electrons and holes in the semiconductor. At the same time, they have a chance to recombine, so to disappear. Okay, so in that case, in the end, there's two competing process. First is the generation process, and then you have a recombination process. In the end, these two processes will strike a balance. So in that case, the recombination will equal to the generation, and the recombination are equal to the excess carrier concentration divided by their lifetime. G prime are equal to the R prime. So then we have these two conclusions. So first, by setting this G prime are equal to R prime, we would have delta N equal to G prime times tau P 0, or delta P equal to tau P 0, because delta N are equal to delta P. one photons absorbed by the semiconductor will create one electrons and one holes at the same time. So we have these two conclusions. Now, second, let's review what is the current and what is the photocurrent. Let me first give you the definition of current. The current definition is following this: is giving a delta t, a certain time, the number of charges passing through a surface area. For example, a surface area in this gray area. Okay, how many number of charges are passing through this surface at a given time of delta t. Let's suppose if all the electrons, when they're applied electric field, so the holes were propagated at a speed. Okay, that speed is equal to delta L divided by delta t. So at a given delta t, they are transport a distance of delta L. And this speed is actually proportional to external electric field applied. And for physics, we normally write a linear correlation of the two parameters as an equation. So we have the V are equal to mu times E. Mu is constant. Okay. The physical meaning of mu is mobility. Given delta t, all the charge inside this box will pass through this cross-section area. So what we do over here is we use Q is a unit of charge. P0 is a charge concentration in this material, and delta L is a volume inside this box here, and AC is a cross-section area. So the top equation is the total number of charges are inside the box. Okay. And then that divided by, that's the current. So then delta L divided by delta T, that's the speed. Okay, speed are equal to the mu times E. So that is a expression of the current that is equal to unit of charge, the charge concentration, the mobility, the electric field intensity, that's and times cross-section area. The electric field intensity actually equal to the V divided by the length of this material. So in the end, this is Ohm's law. Okay, this is Ohm's law. Okay, but for a semiconductor, to be more general, and we have electrons and holes. So that's why we rewrite this equation as P0 times the mobility of our holes, the hole concentration times the mobility of holes, plus the electron concentration times the electron mobility. Just to replace this part with two types of carriers. So to be more general. Okay. Now, a photocurrent definition is defined as the total current under light illumination minus the current. There's no light illumination. That means your device in darkness. Okay. So for the current in dark, we already write the expression that is written as this. For total current under light illumination, the only difference is under light illumination, you create excess holes and you create excess electrons. So you replace this hole concentration with the hole concentration in dark plus the excess hole concentration, the electron concentration plus the excess electron concentration. Okay, basically the equation is the same except that these two parameters are different. Okay, so then in the end we plug these two equations back to here, and then we basically can cancel this the P0 and N0. Basically, we can cancel that. That's what we get, the photocurrent. Then the photocurrent will write as Q times the mobility, hole mobility times excess holes plus the electron mobility times excess electrons times the electric field intensity times the cross-section area. So that is the photocurrent. Now, the next thing is the number of photons and the photo carriers, how we're going to calculate that part. So here, first, we have to understand what is the light intensity. Okay, light intensity is defined as this: the number of photons per seconds per unit area, okay, times the photon energy of each photon. That means if the giving a limited area, you have more number of photons passing through this area per seconds, then the light intensity will be higher. If the light photon energy is higher, that means the shorter wavelength, then the light intensity will also be bigger. That is the definition of light intensity. So giving a light has a wavelength of lambda. Each photon, suppose, have a photon energy with h bar and times omega, or h times mu. Let's suppose all the light, okay, will be absorbed by this semiconductor. And the semiconductor has a volume of V that is equal to the cross-section area times the length, okay? And the top projected area in the direction of the light incident direction. The semiconductor has a surface area of cross-section area project, that's projected in the direction of light illumination. So now the photons per second absorbed by the semiconductor. So basically, light intensity divided by each photon energy. So then that is what we get over here is the total number of photons, okay, per unit area. Then we times the semiconductor area projected in the direction of the light illumination. Then that means there are how many number of photons that are actually instant on the semiconductor. And we assume all the instant photons are absorbed by the semiconductor. So each photon will create each one pair of electron and holes. Okay. So in that case, we have the photon carriers per seconds per volume. That is the generation rate, G prime. That's what we learned previously. Light illumination or semiconductor, you have a generation and then you have recombination. So this generation can actually be divided as what? The total number of photons absorbed by the semiconductor and then divided by the volume of the semiconductor. So inside the volume of semiconductor, how many number of photon will create one electron, the one hole. So in that case, that's our generation rate, okay, per seconds, per unit volume, how many number of carriers are generated. Now let's come to the classical gain theory for photoconductors. That actually was first derived in 1956. Okay, so the definition here is following the G equal to the G in quantum efficiency equal to the total number of charges are collected by the photocarriers, collected by the electrodes, divided by the total number of photons are absorbed or instant on the semiconductor. Okay, so following these two expressions over here, so basically at the photocurrent, you can write it in this expression, plug this equation back over here. Okay, and then we have this Q, put it at the bottom. So this Q and the Q are canceled. Okay, and then for the cross-section, A projection area and times light intensity divided by H bar. So that is this part are actually equal to the G prime. Okay, we replace this part with G prime times the volume. That's equal to the L times the cross-section area. So basically, we can cancel out the cross-section area, cancel out the Q. So we can derive the equation by assuming delta N are equal to delta P, because one photon will create one electron and one hole. So the number of electrons, the holes in the semiconductor are always equal. So we have delta N equal to delta P. So in that case, we can write delta N, this equation as delta N, and then the other part, this is also equal to delta N. So this expression are simplified based on this assumption. Now we can further make assumption over here is delta n are equal to the g prime times tau, right? G times tau. So that for that reason, so we replace this delta n with g times tau, and we are then in the g generation rate, actually it canceled and canceled over here. So then we have this equation. We can further simplify this equation over here by using a transit time. This transit time are equal to the L, the length of the device, divided by the E times mu n. The electric field times mu n are equal to the speed. That's what we defined before. So a higher electric field, the charge carrier will transport at a higher speed. So this defines as transit time. Tau over here is a minority carrier recombination lifetime. Okay, that's what we also defined previously. That's directly related to the recombination rate. Yeah, recombination rate are equal to the delta n or delta p divided by the minority carrier lifetime. That is this parameter. Okay, so this is a classical gain theory of photoconductors. Okay, and this theory has been widely accepted in the research community. Okay, so for example, in the textbook, there is a English textbook, is a pure English textbook actually, is a Semiconductor Physics and Devices, Basic Principles, fourth edition, actually edited by Professor Donald Niemann. Okay, so on page fourth edition, page 634, so you have this equation. So the gain are equal to the tau p, which is the minority carrier lifetime, divided by tau n. Tau n is a transit transit time for charge carrier transport from left side to the right side, and this is exactly the equation we derived. And there is another famous textbook, okay, which is Physics of Semiconductor Devices, edited by Simmons Z. On the page 669, so we have this equation. This is also defined as the gain. We have this equation. This is electric field intensity, and simplified. The only expression that is a little different over here is basically they define the transit time for electrons and transit time for holes. So that is essentially this is the same expression, but just write it in slightly different. Okay, that is exactly what we derived. How can we understand why a pure semiconductor, when they're in contact with two metal electrodes, and then you apply electrical field under light illumination, then there is a huge gain. This gain can be easily reached 10 to 3, 10 to 4, 10 to 5, even the highest number reported in the literature is 10 to 10. Okay, so that is like 10 to 10 is 10 billion times. Okay, so basic understanding the concepts over here is widely accepted concept is light, and you generate electron pairs. Okay, one type of excess carriers were actually trapped by surface states, and the trapping time can be very long. And then the other type of carriers will be driven by the electric field, circulate in the circuits many times before, because the electric field applied is very big, so they can transport very fast, so they can circulate the circuits in a very short time. And the surface trapping, the process is normally very slow. So when they trap and they start to detrap, this time will be very long as seconds or hours sometimes. Okay, so that's why you have a very high gain. Following our previous definition, the minority lifetime over here can be very long, because we believe is the trap lifetime. Okay, and the transit time is very short. So that's why the gain is coming from here, and not coming from the mobility difference between the electron holes, which normally is a very small number, just a few, maybe 3. For silicon, for example, 3. Actually, the electron mobility is higher than the hole mobility. For example, in this case, is actually the mu p divided by mu n is equal to 1/3. Is smaller than 1. So the gain cannot be coming from this difference in mobility. But In 1948, Japanese scientists carefully investigated this theory, and they actually measured the minority care lifetime, this tau p, and they also measured their transient lifetime, and they plug the equation over here, like I said, because there is another parameter 1 plus mu p divided by mu n, or mu n divided by mu p. The later term, the difference of mu p and mu n is very small. It's not big number. Okay, so actually we can ignore that part. This equation over here, if we carefully calculate that part, so the Japanese scientists calculate that part, they find the tau p are equal to 10 to minus 8 to 10 to minus 10, have a certain uncertainty, but it should be in this range with very high confidence. And the transit time 10 to 9. So for detectors, okay, so in this case, what they find is the gain calculated from equation 1 is about 10 at most, not higher than 10. It is clear this model cannot explain the experimental results, either for the value of the gain or for its dependence of photon flux intensity. What I mean is, in experiments, very often we observed this sort of phenomena. So the gain is highly dependent on the light intensity. Okay, highly dependent on light intensity. So when the light intensity increase, the gain will quickly drop. Okay, from, for example, here is for 10 to 7 to 10 to 4. Okay, and this cannot be explained by the classical theory. Okay, but even though in Japanese scientists has challenged this theory, scientists are trying to explain away this theory in different forms, different like explanation. And so this equation, this theory is still widely used even today. So for example, there are many papers. I choose one that's very typical, is 2006. Okay, so they're using this theory to explain their experimental results. Okay, and there's another paper published in Nature Nanotechnology also uses this theory, explain their new device. Okay, so that means this theory is still widely used, widely accepted by the research community, although it has some inconsistency. Now, the second part of this talk, I'm going to present our recent finding that a photoconductor intrinsically has no gain. In order to introduce my research, okay, let me first tell you the basics of the energy band of semiconductors, metals, so that we have a deeper understanding what happened inside the semiconductor and inside the metal. So here is the K-space, the band structure in K-space. If you're not familiar with this, forget about it. We can only look at about this part. Okay, look at this part. This is the physical space. For semiconductors and metals, they have, for semiconductor, it has this sort of the energy bands. Okay, so it has a completely filled valence band. Its valence band is completely filled. Okay, with electrons. Okay, while the next band on top of the valence band is actually separated by a gap, and this band we call the conduction band. And the conduction band is empty, in particular at zero temperature, is completely empty. So now in this case, still at the absolute zero temperature or close to absolute zero temperature. Now, if you apply the electric field over here, electric field, of course, trying to accelerate all the electrons in this material. So the electrons will experience a force trying to be accelerated by the electric field. Okay, because if the electrons receive energy from the electric field, the electrons will move to a higher energy level. The electric field is continuously drive the electrons. So the electrons will receive a minimum amount of energy almost continuously from the continuous energy from the applied electric field. But look at it here. The electrons in the valence band are all occupied. The next available energy level allows the electrons to gain energy to move higher energy level is separated by a gap, which is the band gap. That means unless the electrons receive an energy that is higher than the band gap, otherwise these electrons has no space to move up. Okay, because their band in this continuous band are all completely, although I plotted in a discrete energy level, but in reality is they're almost continuous. They are completely in the field with electrons. So in that case, that means these electrons in the valence band cannot receive a minimum energy from the electron field. Cannot receive that energy. That means the electrons cannot be accelerated by the electron field. If the electrons cannot be accelerated by the electron field, what that mean? That means this material is not conductive. So yes, at very low temperature, close to absolute zero temperature, semiconductors is not conductive because the electrons cannot receive a minimum amount of energy from the electrical field to move a next available energy level, which should be very close to the highest energy level of the valence band, but they're empty. They're separated by a gap. Okay, so no electrical energy can be received by electrons in the valence band. Okay, but if we illuminate the semiconductor with photons, okay, photons has a quantized energy. It's not a continuous minimum amount of energy. And if this energy is higher than the band gap, okay, then the electrons can receive this quantized photon energy and jump to energy level in the conduction band, because in the conduction band the energy level are empty. So once they receive this energy, so they will go higher, and this gap is equal to the photon energy, right? And once the electrons jump to the energy level in the conduction band, now they can be now this electron can be accelerated by the electric field, because now these electrons can receive a minimum amount of energy from the electric field, so that they can move to next available empty states, which is just above the conduction, above this energy level. Okay, their distance is very small. You can regard this as a continuous energy level. Okay, so in that case, the semiconductor becomes conductive. Okay, we call this is excess carriers. We create some excess carriers in the conduction band. Okay, the excess electron in the conduction band and excess holes in the valence band. Now, if you create excess holes, so the electrons below this unoccupied energy level can receive energy from the electric field. Now, these electrons can also become conductive. So normally we regard this as a hole conductive. Okay, is a hole conductive. The hole can receive energy. They can move to lower energy level. Okay. So we create excess holes in the valence band. So in that case, the semiconductor becomes more conductive. Okay. Now let's take a look at the metal. The energy band from the metal. Metal has a particular band structures. It has partially filled. The highest energy level is in the band that is partially filled. Unlike semiconductor, this energy level, this band is empty. Okay, is actually partially filled. Now think about that. If this semiconductor is, if this metal is, this band is partially filled. Now apply electric field. The electrons inside this band, these electrons receive the energy from the electric field, moving to next available higher energy level. This energy level are continuous. Okay, minimum of, they only need a very small amount of energy so that the electrons can move to a higher energy level. So that means these electrons can be accelerated by electric field. And they're conductive. So yes, metal at absolute zero or close to absolute zero, the electric field, it is conductive. Semiconductors is not conductive unless you illuminate it with light. Now, same thing happened. If we illuminate light, the electrons in the conduction band can be excited to a higher energy level, okay? But the total number of energy level in this conduction band doesn't change. While of course the valence electron in the valence band, they has a possibility actually increase the energy level, actually has a possibility receive the energy from the photon and jump to a higher energy level. But for metals, this band is partially filled. So unless your photon is extremely high photons, extremely high energy, so otherwise, when there are energy level higher than that, because there is a energy level, many part of the energy level in this region are actually occupied with electrons. And then the energy level from the valence band cannot be excited into the conduction band because the band in the very wide range, this energy level already occupied by electrons. So the electrons at the bottom cannot excited to the top one, and there's no space, no empty space for the electrons to occupy because they're already occupied by electrons. Okay, so in the normal case, they're not conductive. So in the normal case, metals will not become more conductive under light illumination. Okay, so there's no photo excited carriers. The delta N equal to delta P equal to 0 from metals. That's the reason. Okay, only the electrons in the conduction band can be excited into higher energy level, but the total number of electrons in the conduction band are the same. So there's no excess carriers. Okay, now with this this information, this knowledge over here, now let's photoconductors. Now a photoconductor, like I said, is a semiconductor contact with two metal electrodes, and the semiconductor metal, we assume they're from ohmic contact, is purely conductive device. Okay, and now under light illumination, in the semiconductor you create excess carriers. Okay, but inside the metal there are no excess carriers. Okay, the excess carrier delta P must be spatially continuous. Okay, should be continuous. It cannot be have one case have electrons, a lot of electrons, the other suddenly becomes 0. That's not going to happen, because if that happens, then the electrons will diffuse to the other side. Okay, will diffuse to the other side. So under light illumination, what happens over here? Inside the metal, there's no electrons, no holes. And semiconductor, we have delta N or delta P at the same time. And to me, the excess carriers are continuous. So in the end, the metal semiconductor interface confinement will force the excess carriers inside the semiconductor to be non-uniform. Okay, to be non-uniform. Maybe at the very center, if the device is very long, and in the middle part, then this is equal to delta N. Is like is not affected by the interface, this metal semiconductor confinement. But when they're getting close to the surface, close to the interface, the excess carriers would reduce, and in the end, we equal to 0. That is what happens. Applied electric field, this non-uniform distribution, spatial distribution of excess carriers will actually tilt because their distribution is different. So they will change. Okay, they will change. So to find the analytical expression of the excess carriers, their spatial distribution. So we have to solve the continuity equation for minority carriers, and that's what we find. Although the expression look a little complicated, but we can find it. Okay. And the analytical expression we also, that's the analytical expression for minority carriers. We can also use commercial software to do the simulation. So in that case, we can solve the continuity equation for minority carriers and for majority carriers, both of them. And the results are pretty similar. So this is the red line is the simulation results, the black bar solution from the continuity equation. And that's how the excess minority carrier distributed in the semiconductor, which is 2 at the metal semiconductor metal interface. There's no excess carriers. Excess carrier will equal to 0. Okay. Now we apply the electric field over here as we expected. So then actually the excess carrier will tilt. Okay, as we increase the electric field. So that means what? It means previously we make assumption that delta n are equal to g times tau. Take a look at this equation. Delta n is not a function of space. That means spatially they are uniform. Delta n is not a function of the electric field intensity. Okay, that means whatever the electric field applied, their distribution is still the same. Okay, this equation delta n equal to g times tau are only valid when there's no boundary confinement. If there is boundary confinement, this equation is not valid anymore. Okay, so the classical gain equation is questionable. First, the delta n equal to g times tau, this equation is not valid. Okay, is only approximately when you are applying when the device is very long, okay, or we are not applying very big electric field, then this delta n will approximately equal to delta g times tau in the middle part of the semiconductor. That can happen. So that's so when you calculate the current, so that is the photo current actually is not a linearly increase with the electric field, because the excess carrier, when you increase delta n will increase electric field, the actual tilt will become less. So that is the classical theory, and that is the reality. The photo current will be saturated, will tend to saturate like as you increase the electric field. Okay. Now we also calculate the actual the gain, the photo current, and the gain. We do the gain calculation. So we find this. The gain is indeed not larger than 1 when the for example, the mobility of the holes, which is a majority carrier, smaller than the electrons. So in that case, then the gain will be never higher than 1. If the mobility are equal, then as you increase the electric field intensity, the photo current will saturate, and the gain will approach to 1. When the mu p is larger than mu n, the gain actually can be larger than 1, but it's still much smaller than this ratio. Okay, it's still much smaller than the ratio, not higher than this ratio. So only a few times of that. Okay, so that means what? That means ideally, strictly speaking, a photoconductor will not have a gain, or at least it will not have high gain. That's our conclusion. But in experiments, scientists, engineers indeed observed a high gain in experiments. This gain is real. Now the question is, where is the gain coming from? How is that possible? There is a high gain. Okay, due to limited time, I'm give you a very short conclusion over here. So the conclusion over here is that's because the second assumption delta n are equal to delta p, that's also not valid. Okay, for a real device. Okay, for a real device. Why? Let me give you an example. So previously we have this. We are thinking about a semiconductor and light illuminate on the semiconductor. The one photon absorbed by the semiconductor will create one electrons and one holes, right? So that's why we have the conclusion of the excess carry excess electrons are equal to the excess holes. Delta n are equal to delta p. Okay. But in reality is this, in particular for nanoscale devices, surfaces are actually dominant. We know the surfaces are where the dangling bonds are terminated. These covalent bonds are terminated from these dangling bonds. If there is dangling bond exists, they form surface states. Okay, the surface states will be charged. For example, an N-type semiconductor, electrons is the majority carriers, and the surface will be filled with electrons, so they will form a negatively fixed charged surface states. This negatively fixed charged surface states will form a depletion layer near the surface, will push away the electrons. Okay, formation region near the surface. Now the same thing happens. Now if you light illumination illuminate over here, then you create one electrons and one holes, no problem. But because the band is banded near the surface, what happens is the excess electrons will move towards the center inside the channel, and the holes will actually accumulate near the surface. They create electron holes separated. Okay, so you can think of that. So you will create a lot of electrons, accumulated holes, a lot of holes accumulated in the channel. So in that case, but the current is only flow inside the channel. It will only flow inside the channel, and the charge carriers are electrons. So when we are counting the photocurrent or calculating the conductivity change, or when we measure the conductivity change, we actually measure the majority carrier change, the concentration change. The excess majority carrier change is only, this change is only coming from the extra electrons, not extra holes. Okay, because the holes are actually separated by the depletion region. So there are physical, spatially, they are located near the surface on the other side of the depletion region, and not inside the conduction channel. And the photocurrent only coming from the delta P, not from delta N. Okay, so but that's why when we calculate the photocurrent, we cannot assume delta N are equal to delta P. No, when we calculate the photocurrent, delta N are not equal to delta P. Now, for more reading, have a deeper understanding on this, please read my other two papers. Okay, one is published in ACS Nano 2018. Another paper is published ACS Nano in 2020. In these two papers, we address this issue with very solid experimental and simulation evidence. So now coming back to the original classical theory derivation, since we cannot make assumption delta n equal to delta p, and we cannot make assumption delta n equal to g times tau, what we can do is we only make assumption over here is this is delta n are not equal to delta p, so this is not cancelled. Okay, this is not cancelled. And the g times tau, well, when you are not applying very big electric field, strictly speaking, delta n are not equal to delta tau. Delta n not equal to g times tau. But when you're applying, when the device is very long, we're not applying very big voltage, you can still make that assumption. It's close, no big difference in that case. Okay, but in anyhow, so in that case, when your electric field is very small, so that means this tau transit will be very large. You will not create a situation is this minority carrier lifetime much larger than the transit time. No, because when you are applying big electrical field, this delta n will become very small. Okay, so this number will also become very small. This equation is only valid, this part is only valid when your device is very long and not applying very big electrical field. Okay, so in that case, this first parameter, tau effective divided by tau transit, this number is not going to be very big. Okay, so that means gain should not come in from this difference, this two, the difference of these two parameters, or the ratio of these two parameters. The actual gain actually coming from this difference. The inside the channel, the majority carrier accumulation, okay, the majority access carrier divided by minority access carrier, that difference can be very big because the surface separation will actually allow the majority carriers, access carrier, accumulate in the channel, while the excess minority carrier will be separated into the surface of the depletion region. So that inside the channel, the number of excess minority carrier actually very small. The number of excess majority carrier can be very big because it can accumulate over time. So the action in the end, this gain is coming from this parameter. So strictly speaking, we should have a gain equation following this expression, and the gain is coming from this g prime, not from here. Okay, so as conclusion, so the classical gain theory is derived on two misplaced assumptions. After we correct the assumptions, we find a photoconductor intrinsically has no gain, or at least no high gain. Photogain are coming from where? Are coming from the accumulation of excess carriers inside the channel. So in the end, I'd like to thank my group members who contributed this work and our funding agent. And thank you.